Hello and welcome. In this video, our topic is the polar and rectangular representation of a sine wave. To understand why we even need this math, we first need to look at how electricity behaves. In a standard DC circuit, the voltage is completely steady, like water flowing evenly. But in an AC circuit, the magnitude of the voltage is constantly changing due to the way it is generated. As time progresses, this alternating current creates a sinusoidal wave. If our AC circuit only has a plain resistor, things are simple. As you can see, the peak of the current and the voltage happen at the exact same time. They are completely in phase. But this changes if we introduce an inductor. Due to the way an inductor works, it resists the change in current. This causes the current to be delayed, or lag behind the voltage. The waves are no longer synced up. This horizontal gap between the peaks is what we call an out-of-phase delay. Because the inductor slows things down, the current wave reaches its maximum point a fraction of a second later than the voltage wave. To represent this delay mathematically, regular numbers aren't enough. We need a system that can track two things at once: the size of the wave and the timing of its delay. To do this, we use two different forms. The first way is the rectangular form. Think of it as mapping the circuit's physical resistance on the horizontal real axis and the inductor's delay effect on the vertical imaginary axis. We write this mathematically as Z equals A plus JB. Plotting A and B gives us a specific point on a grid. But to really understand the wave, we draw an arrow from the center to that point. In engineering, this rotating arrow is called a phasor. This brings us to the polar form. Instead of grid coordinates, polar form directly measures the length of that phasor arrow, the magnitude, and the exact angle of the delay. We write this as Z equals R at an angle of theta. Let's build an interactive example. Imagine we wire up a standard resistor that has a resistance of 3 ohms. Right next to it, we wire in an inductor that has an inductive reactance of 4 ohms. How do we write this circuit's total impedance? The resistor doesn't delay anything, so its 3 ohms go purely on the real horizontal axis. But the inductor creates a 90-degree phase shift, so its 4 ohms go on the imaginary vertical axis. This gives us our rectangular form, Z equals 3 plus J4. To find out what this actually does to our sine wave, we need the polar form. We find the total magnitude by finding the length of our phasor arrow. We use the Pythagorean theorem. The square root of 3 squared plus 4 squared equals a total magnitude of 5 ohms. Next, we calculate the exact angle of the delay. We take the inverse tangent of our imaginary 4 divided by our real 3. This gives us an angle of 53.1 degrees. Our total polar impedance is 5 at an angle of 53.1 degrees. What does this actually mean for our circuit? It means if we push a voltage sine wave through these components, the total resistance fighting it is 5 ohms, and the resulting current wave will be forced to lag behind by exactly 53.1 degrees. We used rectangular to build the circuit and polar to see the result. Thanks for watching.